Dear students, welcome back to Theory of Computation lecture video sessions. This is Dr. K. Praveen Kumar, Department of IT, Assistant Professor. Today, in this lecture video, we are going to discuss about central concepts of automata theory. For that, the textbook, you have to use the prescribed textbook, John E. Hopcroft, Rajiv Motwani, and Jeffrey D. Ullman, Introduction to Automata Theory. And it is mandatory to purchase your own textbooks. In that topic 1.1.2, we are going to discuss now. Right, lecture level outcome. So upon completion of this lecture, you will be able to apply the concepts of finite automata, basic finite automata concepts you can apply onto the given problem. So central concepts of automata theory is first one, languages. So as we know, to communicate with one person to human or human to machine, you need to have some languages. The languages we consider our discussion in abstraction of natural language. That is our focus here on formal language. You're going to learn the formal languages that need precise and formal definitions. Programming languages belong to this category. So next one is symbols. So symbols are indivisible objects or entity that cannot be defined. That is, symbols are atoms of the world of language. The symbol may be of anything like a arrow mark, 0, 1, hash, and a begin is also a symbol, or do is also a symbol for the programming languages. Usually characters from typical keyboard are all used on the key symbols. Next one is alphabets. An alphabet is a finite non-empty set of symbols. That means there must be countable number of alphabets, and it is non-empty set of symbols. There must be a symbol, and the alphabet of a language is denoted by sigma. Sigma, and alphabet must be a finite, and it must be a non-empty set of symbols. So when more than one alphabets are considered for discussion, subscripts may be used, like sigma 1, sigma 2, etc. Or sometimes the other symbols like G may be introduced. Examples. So sigma is equal 0 of 1. That is, set of symbols is 0, 1. A, B, C, another set of symbols. A, B, C, one symbol, and Z. And these are different symbol, hash, cap symbol, beta. Like that, there are several symbols. They are all examples of alphabets. Next one is strings. Words over alphabets. You know the definition of a string. Combination of alphabets or characters is called as a string. String or a word is a finite. Here we need to note it down. Finite sequence of symbols chosen from sigma. Sigma may be either sigma 0, 0, zeros and ones, or sigma ABCs, or sigma different symbols. And if there is no strings inside sigma, then it is called as epsilon. That is called as empty string. Empty strings are denoted by epsilon. So example for the strings 0, 1, 1, 1, 1, 0, 0, 1 are three strings over the binary alphabets 0 and 1. So here the combination of 0 and 1 we can write, that is called as strings. Right. Length of a string. So the number of meaningful symbols in string W is called its length. So the number of that is finite length of meaningful symbols. Meaningful symbols in a string, a W is called of length of string, and it will be denoted by in a like this. So if you write 1011 in this length of string symbol, pipe symbol, the length will be 4. 1, 2, 1, 2, 3, 4, 4 symbols. 1, 2, 2, length of that string is 1. So if x is equals to ABB, AAB, then the pipe symbol length of that string is 6. And if x is equals to 0, the length of string is equal to 0, then it is called as empty string, that is epsilon. String operations. Consider the string 0, 1, 1 over the binary alphabets, all the prefixes, suffixes. So these are the prefixes 0, 1, 1, 0, 1, 1. So 0 maybe a prefix, 0, 1 is a prefix. Empty string also a prefix. Suffix maybe when you write after that one. So epsilon will be always prefer. You can write prefix or suffix. One is a suffix. This one is a suffix. 1 is also you can call it as a suffix. Or you can also write the entire string also in suffix. And substrings epsilon 0, 1, 0, 1, 1, 1, 0, 1, 1 will be the substrings. So next one is power of alphabets. We write sigma k. K means some number 0 to n number, which denotes the set of strings of length k with the symbol from sigma. That is, if sigma is an alphabet, then sigma k is a set of all strings of length k. So in other words, sigma k is equals to W such that W is a string over sigma and length of W is equals to k. So for any alphabet, sigma 0 is length 0 because sigma 0 means there is no strings inside, no characters inside. So generally we denote sigma 0 is equals to epsilon for all the binary alphabets 0 and 1. And sigma 0 is equal to epsilon, sigma 1 is equals to 0 and 1, sigma 2 is equals to two symbols you can use 0, 0, 0, 1, 1, 0, 1, 1. Sigma 3 is equals to 0, 0, 1. 3 length must be 3, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and so on. So set of all strings over an alphabet, sigma is denoted by sigma star. We can also call it as clean closure. We'll discuss in the next slide. Right? Generally, sigma closure will be denoted like this. So set of sigma star contains all strings that can be generated by iteratively symbols from any number of times. So you can also write like this, the example. Right now, clean closure. So as we have discussed in the previous slide, clean closure is a unary operator, and set of symbols or strings on sigma that gives infinite set of all possible strings of all possible length over sigma, including epsilon. So that will be represented by sigma star. Sigma star is equals to sigma 0 union sigma 1 union sigma 2 and so on. And that sigma will have the character 0 and 1. So clean closure is equals to epsilon 0, 1, 0, 1, 0, 0, comma 1, 0, 1, 0, 0, and so on. All the combinations of zeros and ones. And clean closure plus. The clean closure plus C is when you are writing, it is also similar to clean closure only when you are eliminating epsilon. That is, there must be no empty strings. Then it is called as clean closure plus. So simply you can say that the symbol is sigma plus will be denoted is equals to clean closure minus epsilon is equals to clean closure plus. Right? So this is all about today's CDT, and the reflection point spot for this lecture video is sigma is equals to AB language, L is equals to X belongs to sigma star, that is clean closure, such that such that uh, X is a string combination, and the sigma 4 represents which of the four among following. So AA, AB are this one, or AAA, AAB are all the above mentioned. So students pass here and find the solution. And if you are right, then you can go for the other video. If you are not able to answer right, then please repeat the video again. Solution for answer for this reflection spot is B. That is, here it is sigma 4. So the length of your string is 4. The length of the string is 4. And epsilon is a, you can assume it as a 4 or 5, whatever it may be. So 4 and 4, the length of string, all strings are length 4. So this B is the right answer. So summary, in this lecture video, we have learned what is languages we use in the automata, different symbols we use, alphabets, what is string, and what is the length of a string, power of alphabets, clean closure, and clean closure plus. These are the concepts we have learned in this lecture video. And having completed the discussion on central concepts of automata theory, you should be able to identify the string accepted by the finite automata. So lecture level question for this CDT is list and identify the elements required for the design of finite automata. Thank you. We'll meet in another video session.